In the video introducing thermodynamics, I mentioned how if you have two properties of your system and it's simple and compressible, then you can find any of the other properties. And in this video, we're going to show you how you can do that. We have to start with talking about phases. So our assumption here is that we're talking about a pure substance, which means it has a fixed chemical composition. So basically we have something like CO2, H2O, that's water, but it's just going to have a single chemical composition. It's a fixed mixture throughout. You can have different phases, but it's always the same kind of thing. So if I have, let's say, water and I'm boiling it, I'll have liquid and gas, but it's still just water. So these here are three phases that we're going to be looking at. Solid means basically that it has a fixed shape and a fixed volume, right? There's kind of a set shape, even though they might be, like the molecules and atoms might be wiggling around the equilibrium. Liquid means that it doesn't have a set shape, right? If I fill a container with some water, then it's going to basically take the shape of this water, but it does have a set volume, right? A gas, though, doesn't have a set volume. I can compress it, I can expand it, but I can't do that with liquids or solids, right? We model these as incompressible. The gas has no fixed volume, no fixed shape. It kind of just like is this blob of gas, right? And so this diagram right here is a diagram of two of our properties, temperature and specific volume, modeled over a phase change process. So basically when we start down right here, we've got a low temperature and a low specific volume. Basically this is our liquid phase right here. So along this whole line right here, we'll just call this 1. State 1 is what's called a compressed liquid. Basically it's just a liquid where there's nothing going on, no other phases in it whatsoever. Now as we get closer and closer and closer to the saturation temperature, which you can think of as like the boiling point, then we're going to get to this point right here where it starts to go horizontal. This is state 2. It's called a saturated liquid. Basically, at this saturated liquid, specific volume, and this temperature, if any more energy gets added, it's going to start becoming a gas and increasing its specific volume, but it's still technically at a liquid right here. Now you notice at this temperature, our temperature doesn't increase as we keep going along until we've already hit this point right here. And that's because basically all of the energy that you're adding to your fluid is going into boiling it. So if you think about boiling water, once it reaches the boiling point, the temperature isn't getting any higher above that until it all boils off and it's a gas. At that point, you can go ahead and you can increase your temperature. So between here, what's happening, 3, is called a saturated mixture. Basically, it's going to increase and increase and increase in average specific volume. And right here, while we're all liquid, right here, we're all gas. This point right here is 4. 4 is a saturated vapor. Basically, it's the same thing as a saturated liquid, where if I were to start losing any energy, it would start forming liquid droplets. But technically, right now, it's all a gas. And lastly, we have 5, which is called a superheated vapor. Basically, that just means that all of it is a gas, and it's up here, and you can increase the temperature and the specific volume. Now, this green thing right here is basically what these different blue lines look like at different constant pressures. So this whole system right here, this whole kind of boiling process is modeled as a constant pressure right here. But if you were to do it at some other pressure, then you get some other line that would look maybe something like this. It's a little hard to draw with all the numbers in the way, but you see what I mean? It would look basically the same, except it would be a different pressure. You can go higher, you can go lower, but this green dome basically represents if you were to connect all the saturated liquid and saturated vapor points, you get this dome right here. The point at the very top, kind of right here, is just called the critical point. And basically what's happening here is that once you get to this pressure, there isn't really a distinguishing point between liquid and vapor. Basically, it's just going to increase and increase in both temperature and specific volume more and more, and there isn't this distinction right here. So this right here is VF, it's the specific volume at our saturated liquid point, and this is VG, it's the specific volume at our saturated vapor point. There's other terminology you can see for this, so just to say, versatile, you might also see this as VL for saturated liquid, and I believe it's V for saturated vapor, so this is a different V than this. This is technically the Greek letter nu. These are different, but just think of this. It's V_V, where this is our specific volume, and this is, I think, a capital V for saturated vapor. Now, if we want to, we could also do this with a pressure versus specific volume graph. So if we go down here and I rewrite up my axes, what I can have is basically a pressure versus specific volume graph where I'm looking at a constant temperature boiling. So if I go here and basically I draw the same thing, what we're going to see is that it's kind of inverted. So our pressure will go down like this, it'll go over, and it'll go down like this. And then we'll still have our dome, which will do something like this, where it'll go up and then it'll go down. So as you imagine going through this process, basically what's happening is that as we, let's say we have like a piston cylinder, right? And I got my piston right here. And basically what I'm doing is I'm adding pressure, right, onto my fluid. So basically, when I'm adding pressure, it's going to get more and more compressed as it can become a compressed liquid, and you might even be able to get it to solid if you compress it hard enough. Now if I pull it and I start decreasing the pressure, what's going to happen is that it's going to take up more and more and more space until eventually part of it becomes a gas, and then eventually all of it will become a gas. So basically it's just going to follow this process in reverse, where this is our constant temperature line. We'll still have the same specific volume for our saturated liquid and our saturated vapor points. This right here is now called the saturation pressure, and we'll also have a critical point up here, just like we did before. Now inside the saturated mixture point, there's a certain value that we use to kind of tell you how much of a mixture it is. It's called quality, and the kind of number, or I guess it'd be letter, the variable we use is x. It's called quality. And basically it's equal to the percentage of our mass that's gas. So it's the mass that's vapor or gas divided by the total mass. So if you imagine right here, all of it is gas, so it's going to be 1. Over here, none of it's gas, so it's going to be 0. And so you can also think of x as basically the percentage that we've moved across here. So if I have some point right here, v, this gap right here, as a percentage of this total gap, is also the same thing as x. So another way you can write x is that x is equal to v minus our vf, so this gap right here, over vg minus vf, so this big gap right here. And again, it's between 0 and 1 for our saturated liquid and vapor states. And you can also do this for different diagrams that have different properties. So you could do this diagram with internal energy, you can do it with enthalpy, you can also do it with entropy if you really wanted to, but usually, almost always, you're going to see it as v. These x equations would be the same. It would be, you can always write it like this, but it would simplify it to, let's say, u minus uf over ug minus uf, if that's what you have. And so now that we've kind of presented this theory of how the phase works, we can go ahead and look at our properties. And we're going to do what's called lookups on properties tables. And the best way to show you this is just kind of go through an example. So if I go ahead and I pull up my properties table, we'll go ahead and head up to the top here. You can see I just got this. I'll probably link it in the description. The way this one works, it's a little bit different from what you'd see in the textbook. But basically, what you're usually going to see is there's going to be 3 different tables listed. There's going to be one for the compressed state, one for the superheated state, and one for the saturated state. This table, though, I think it just combines the compressed and the superheated states, which isn't too big of a deal. So let's go ahead and look at an example of how you would use this. Let's say that I'm given my pressure is 400 kilopascals, kPa, and my specific volume is 1.0056 cubic meters per kilogram. And let's say I want to know my temperature. All right. Well, the first thing you would notice is that this pretty much always uses megapascals, so you want to go ahead and convert that real quick. Remember, kilopascals is 1,000 pascals, megapascals is 1,000,000, so 400 kilopascals is the same thing as 0.4 megapascals. All right. Now, when you're going through these lookups, basically what you want to do is always start by assuming that we're looking at the saturated state. So if I go ahead and I go up to this top graph right here, we know our pressure, so we're going to go ahead and look at this constant pressure line, and we're going to assume, starting off, that we're at the saturated state. So if I go ahead and I go down to my saturated tables, if I scroll down, should see table 2. This one's sorted by temperature, but we're given pressure, so we're going to go down. This one's sorted by pressure, so we're looking good. We know we're at 0.4 megapascals, so we're on this line right here. Now if I go back down to my numbers, the specific volume right here is 1.0056 cubic meters per kilogram. So if I go here, cubic meters per kilogram, this just to the -1 just means 1 over kilograms. Notice that they use VL and VV here instead of VF and VG, but it doesn't really matter too much. This right here would be the specific volume at your saturated liquid, and this would be at saturated vapor. Since we have one, or a little bit more than one, and our highest it can be to still be saturated is 0.4, we know that we would be looking at, if we go up to this diagram, we know we'd be looking at the superheated state right here. So this is when you go to the superheated table, but since our superheated and compressed tables are one and the same, we'll just head back up here. Our pressure is 0.4 megapascals. Our specific volume is 1.0056. So we know that our temperature right here is going to be 600 degrees C. So if I go down here, my temperature is 600 degrees C. Let's look at another example. Let's say my temperature is 40 degrees C, and then I'm given quality is 0.95. And I want to know the specific volume, all right? Now, since I'm given quality and it's between 0 and 1, I already know about the saturated state. So I'm just going to go ahead and scroll down to the saturated state. I'm given temperature in this case, so we're going to look at the temperature table right here. Temperature is 40 degrees C, so I'm going to go ahead and look at this temperature right here. Cool, and now I know my X is 0.95, and I want specific volume. So if I go right here, you can see I've got the specific volume as a liquid, and the specific volume as a saturated vapor. This is a saturated liquid. So what I can do is I can just say, all right, my specific volume is going to be the specific volume at the saturated liquid state plus the quality, which is like the percentage of it that's gone to the vapor, times this gap right here. So if we think back to our diagram, what we're basically saying is that my specific volume along this graph is going to be VF plus the percentage it's gone across times how big this gap is. Another way you can think about this is if I'm rearranging and solving this for V, I would have X times VG. Here, why don't I just write it out? So if I want to find V, this would be X times VG minus VF plus VF. And so this is just what I'm going to use right here. If I want to find my, whoa, what just happened there? Some weird happened. This program is kind of annoying. So my specific volume is going to be my specific volume at the saturated liquid state, which is this 0.001008, 0.001008, plus my X, which is given as 0.95, times, I'm kind of running out of room here, we'll just scoot on over, the gap between basically my saturated vapor state and my saturated liquid state. So this 19.515 minus my 0.001008, 0.001008. And notice that this, and this are all in units of cubic meters per kilogram, and then X is a ratio, so it doesn't have units. So my final answer, whatever this comes out to be, is going to be in cubic meters per kilogram. Cool, let's look at one more real quick. Let's say that I'm given temperature is 50 degrees C, and my pressure is 10 kilopascals. And let's say I want to find my specific volume, okay? So we know what to do by now. We're given temperature and pressure, so we go to either the temperature or pressure saturated table. I'm already at temperature, so we'll just go ahead and do that. 50 degrees C, so we'll go right here, and now I'm looking at my pressure. My pressure happens to be 0.012 something at the saturated state. So I guess I should convert this to MPa real quick. This will be 0.01 MPa. Okay, and now notice that this is slightly bigger than 0.01. So if we look at our graph, basically what we're saying is that at this temperature, our pressure is higher than it would be at the saturated level, which means we're looking at the compressed liquid state. So at this point, you would go down to your compressed liquid table, which is also the same as the saturated, or not saturated, the superheated vapor table in our case. So if I come over here and we go down to here and go ahead and get started, we know that our pressure is 0.1 MPa, so that's going to be right here in this zone that we're looking at. And we also know that our temperature is 50 degrees C. So if I come here in this region, temperature is 50 degrees C. So I'll go ahead and look at my specific volume. It's going to be this number right here, 14.867. 867. Okay. Now let's say that I was given the saturated points. Like let's say I know that my saturation temperature is here, and then I also know that my psat is here. What would my specific volume be in this case? Well, we actually wouldn't have enough information to tell. Basically, the way that you can kind of think about this is that the pressure and temperature are dependent of each other when we're talking about the saturated state. If you remember, we need two independent intensive properties in order to define our system. So in this case, our pressure and temperature at the saturated point aren't quite independent, at least in the saturated case. You could actually draw like a little graph of them if you wanted to. Basically, what it end up looking like is there'd be some kind of curve if you plot one of them and the other one. So if you had temperature saturation here, saturation, man, this program, and psat, it would look curved kind of like this. Maybe not exactly like this, it might go the other way. But basically, once you hit the saturation state, you can change your psat and tsat and kind of jump between these lines and then keep going along here, which means that we need more information if we wanted to tell, right? Like when we're talking about this one that was at the saturated state, we're given x, which means we know how far along this line we are. But if we're just given p and we're given t, then all we know is that we're on this line. We can't really tell where we are. But let's say we're given something really weird where we have a table that's like, all right, let's say I'm given t equals like 57 degrees C. That's a really bad 5. 57 degrees C. What am I going to do in this case? Well, the problem here is that our table doesn't really tell us what to do here, right? We have 55, and let's just go ahead and say we're looking for, I don't know, my P in this case, right? So I know that I have temperature is 55, and then my P is, what is this, like 0.0158. And then I also know at 60 degrees C that I'll have 0.0199, right? 0.0199. So basically the problem we have is that our data looks like this, right? Basically, if we've got like, this is T and this is psat, these are both saturated. I know from my data table that, all right, this is 55 and I've got a point right here, right? 55. And then I also know at 60 that I've got some other point right here, but I'm looking for what's the data right here. And so this is an important problem in math called interpolation, where basically we have this discrete data and we need something in between it. If you really wanted to go crazy, you could like cubic spline this thing, but for our purposes, it's usually just going to be fine to go ahead and do a straight line called linear interpolation. So you have your 2 points right here. You can use point slope form to find this. So going through this real quickly, we can get our slope as rise over run. So this would be 0.0199 minus 0.0158 all over, this would be 60 minus 55. And then our equation is going to be y minus y1. Here, let's go ahead and shift this over a little bit. All right. Y minus y1, let's just pick this to be our y1 and x1. 0.0158 equals m, which we know, times x minus our x1, which is 55. We know our x is 57. We know our m, we can plug this in, and we can just go ahead and solve for y, which would be the psat in this case that we're looking at. One important caveat that I forgot to mention here is that these tables are going to be species dependent. So in this case, I kind of just assumed that we were looking at water. These properties are for steam, so this would be what we're looking at in this case. But if you're given a different fluid, like, I don't know, refrigerant, R134A is a pretty common thing to look at in thermodynamics, then you need to find a table for R134A or something like that. Now in the real world, obviously, you're not just going to have a ton of charts that you're looking at and these tables, like looking up through all of them. I mean, at this point, there's enough computer software out there that, you know, you're probably going to be looking at something automated on a computer, and that's exactly what we're looking at here. This is called ease. It's basically an equation solver. It solves systems of equations up to like 12,000 or something, I think. They can be differential equations, all sorts of crazy stuff. And it's pretty simple. The way it works, basically, is you just define variables the way you would if you were using some other programming language. So let's say I want to define a pressure, call this P1, and then I can just set it to whatever I want. So it'd be like 750, okay? Now if I want to put in units, since this tracks units, what I have to do is basically inside square brackets, I just type in, so let's say I want kilopascals here. I can do other things. I can do like temperature, T1, let's say, equals 50. Maybe make this Celsius. We can do other things. There's all sorts of units. If you want to see all the units, you can just go up here, option, and there should be a unit conversion info. This will tell you about literally every kind of unit you'd want. Power, they've got watts, horsepower, all the kinds of watts, everything. So yeah, if you want to convert to them, I believe there's a function for that. You can find all the function info here. It's pretty neat. Like here's all this stuff. What we're really interested in for thermo is these kind of functions, because you can do stuff like, let's say I want to find the internal energy. Remember that I need two independent intensive properties to do that. I can also pick my fluid since that's going to matter. So I could look at, I think there's water if you go all the way down to the bottom here. Yeah, so it can be like water. Let's say I know the temperature and the pressure in this case. That's going to be getting something right here. I can go ahead and I can copy this and paste this into here. And then I can say my T equals T1 and my P equals P1. Now what you do want to check before you do this is that your like unit system is correct. So like right here I have SI, mass is looking good. This is kilograms, Celsius, kPa, kilojoules. Degrees is fine. This is usually what you want for something like thermo. You could also use Kelvin, but since I put this in Celsius, it'll just be easier to do it that way. And if I go up here to say calculate and solve, it's going to solve all of this. It's basically going to do your lookup for you. And you can do, again, you can look up tons and tons of things. You'd have plenty of equations in here. One thing you do want to do is make sure that your things have units. So if you ever have something that you can't really define as units, because you don't just want to come here and like force the unit usually, it's better to like go here and say, all right, I want this to have kilojoules per kilogram. And the reason we're doing per kilogram is this is specific internal energy. If you go up to the function info, you can see right here, it's kilojoules per kilogram. So that's usually the output you want to give. Now if you do calculate solve, it should say, yeah, no unit problems. Now there's other stuff you can do with this. If you want to, you can create a table. So let's say I want to vary my T1, right? What I can do is I can say if not in a parametric table, then set this T1, otherwise it's going to do it anyway, and then we'll need an end if right here. So basically, if we're inside the parametric table, it's going to let this value be whatever it wants to be, otherwise we can just set it right here. This is going to keep the variable in the program when we go to track it. So if I go to tables, new parametric table right here, I can put in my values that I want to look at. Let's say I want to vary T1 and I'll look at what U is, right? So I can stick these in the table right here. Now if I click on this, it's going to let me change the values from 1 to 10. We can just say, all right, I want my first value to be maybe 50 degrees C, and then my final is like 200. This is just going to give me a linear interpolation between those. Interpolation might not be the right word, but it's just a linear pattern, right? So this is going to go from 50 all the way up to, if I scroll down to the bottom, 200 right here. And now what I can do is I can go calculate, solve table, hit OK, and that's going to solve the internal energy for all this. Another thing you can do is you can just plot all this data. So if you need to like quickly get out a little plot so you can kind of see this data, you just create a new plot. We'll do an XY plot, pretty simple. X-axis is T, Y-axis is U. Bada bing, bada boom. You get a pretty interesting plot. One last little thing, I was going over a spiel of like how you would do this in a real program, is let's say you want to get like a diagram of your properties, right? Like a TV or PV diagram that we're looking at. There's a button right here that'll actually just do it for you. So you'd be like, all right, let's say I want water, right? I can have my P lines, I can have my V lines, all of that. I just hit OK. This is a TS diagram. I don't want that. Let's say we get PV. Boom. There's your PV diagram right there. So yeah, overall, it's a very fast way to do this. Lookups are usually a lot faster when you can just type in like, you know, H equals the enthalpy of, let's say, water, T equals T1, and P equals P1. Right, and then you just come over here, calculate, nope, not solve table, calculate solve, and you're done. You need to put in units here probably just to make everything not have like a problem right here. But it's a lot easier, especially if you've got multiple steps and things like that, and you don't want to go looking through the table. One of these programs is probably what you'll be using.